Hello, my name's Richard Hasty. Thank you for the introduction. I'm the Enterprise Business Development Director for EMEA, and obviously I get involved in all of the nice, interesting activities, Ceph being one of them. I think this technology has real potential and is a really cool product. But today, what I'd like to try and cover is who are Mellanox, because historically most people don't know about us as an organisation, and really what does interconnect and networks have to do with Ceph, and why is it relevant? The benefits of having a high performance in interconnect when you're using things like Ceph. What would be typical deployment scenarios, and what have we seen being done in practice? And then the work that we're currently undertaking with the Ceph team in terms of taking Ceph, or the performance of Ceph, to the next stage, really. And then I'll finish on some live commercial implementations and solutions that are available in the marketplace today. After that, I'm going to hopefully take about 20-25 minutes to do that, which will give us about 5 minutes for Q&A at the end. Okay? So, for those that don't know, Mellanox is what we describe as an end-to-end connectivity company. So, we're not a Cisco, we're not an Arista because they just do switches, we're not an Emulex, a QLogic or Intel because they do NICs. We actually do everything from the NICs, the switches, the cables, the optics. We own 2 photonics companies. And we also develop the silicon, which is actually one of our key differentiations. We own all our own intellectual property, so that enables us to kind of do some pretty clever things with stuff that is beyond the norm of what you would typically get to see from merchant silicon. So a classic example is all our technology does or has the ability to do VPI, which is the ability to do Ethernet, InfiniBand and fibre channel over Ethernet, all in the same chip. So you can pick and choose what poison or what networking technology you may want to do at any one time. We wrap all of that with our own, the typical stuff that you would see from an organisation like ourselves, which is all the software layer, all the management layer, all the accelerators. So actually, we do exactly what we say on the tin. We do provide end-to-end connectivity. We're not a small organisation, but we're not a huge mega organisation like Google. We're about roughly on any day-to-day, somewhere between $2.5 billion in terms of market cap. So we're big enough, we're small enough to care, but big enough to cope is how I tend to describe it. So why is the interconnect relevant? So I'm going to start with a little bit of anecdotal or a quote. At the end of 2013, in 1 minute, so put that in your mind, there is 640,000 gigabytes of data transferred over the internet, okay? And actually, conceptually, that doesn't necessarily, to some people that seems big, some people that may be small. But in reality, this is actually growing exponentially. Whether that's being consumed in lots and lots of different object-orientated ways, whether it's sound files, movies, MP3s, email, whatever it is, it's flowing around there and it's literally growing on a day-to-day basis. And ultimately, that's got to be stored or served or delivered from somewhere. And the storage systems or the storage layers that actually allow that to facilitate have to be able to cope and actually scale with those kinds of demands and that growth demand over time. Because you don't buy a storage asset for 6 months or 3 months. It normally has a very, very long investment cycle associated with it. So the Mellanox portfolio actually started with 10 gigabit. We're now at 40 gigabit and 56 gigabit, and by the end of the year we're going to have 100 gigabit down a single cable in the marketplace. So essentially we do big fat connectivity pipes, and that allows us to do some quite innovative things. So just to put it into context from a storage perspective, there's typically two types of ways of scaling or growing storage assets. You can take the scale-up approach, which has been the historical way to do it. I'm ex a very large storage vendor, and I've seen this over many, many years, that actually you buy a big monolithic array. You may only use 20–30% of it day one, and then you start to fill it with cards and disks and other things as you scale that up. But ultimately, you are only as good as the slowest ship in the convoy, whatever that may be. It might be the bus, it might be the drive, it might be the interconnect, it might be the interfaces, whatever that may be, you can only ever scale as far as that. And that's why scale-up storage technologies has effectively started to become less appealing to organizations in the marketplace over time. The alternative is obviously scale out. It's that Lego building block approach to scaling out storage assets. You tack another one in, you plug it into the interconnect. You need a bit more, you tack another one in. And the performance and the scalability actually scales every time you add one of those Lego bricks or building blocks into the architecture. And Mellanox has seen this over many, many, many years. We build very, very large high-performance clusters, and that's our pedigree. And we now do that into like 30,000 servers in terms of scale out, and we have to build the interconnects that allow that to talk. So we have a very long pedigree in doing this kind of stuff, and it's all about making sure that you scale your stack. And when I say the stack, it's the software, it's the processing power, it's the operating systems, it's the drives, and ultimately the network as well, so that they all scale together. And that can be quite a tricky balancing act, but ultimately that's what's going to give you the most benefit and ultimately the best return on investment. So that's a bit of a long-winded introduction, but in truth, interconnect is very, very important when it comes to Ceph, because in reality the interconnect is one of those potential gating bottleneck areas, and it's got to be put into context of how you use Ceph. So it's not just about getting the data in and out of the Ceph cluster, because that's one use of the interconnect, but it's also the communications in the actual Ceph cluster itself, because the communications around the OSDs or the open storage daemons are probably 2–3x more than what you're trying to do on the front-end network, or what data you're trying to get in and out of the storage array. So this diagram, or the actual graph here, is trying to illustrate the impact of the front-end and the back-end network. So the front-end network is essentially the client data, okay? And the red, so the blue bar is essentially the client data. The red is essentially the communication data of just keeping the Ceph cluster operational with the storage assets. Now, of course, you can go and build this all on one single network. That's absolutely fine. And in this diagram, you can see what a typical 10 gigabit Ethernet single cluster network and connectivity pipe would offer you. As you can see, you're essentially, potentially, based on your workload, crippling the performance scalability of your actual Ceph cluster. If you disaggregate the back-end network, or the communication network that Ceph uses, away from the client data, and put something in a little bit more performant, then obviously you can start to scale significantly. So the other bar is actually showing a 40 gigabit network connecting a couple of nodes, whilst maintaining a separate 10 gigabit network for the actual client data. And as you can see, you have huge scalability benefits in taking that architectural approach. And this is what we tend to do. So essentially, your public network and your cluster network are discrete and separate. They can live on the same physical infrastructure, but they're effectively treated as separate networks as far as the Ceph cluster is concerned, and that offers you huge benefits. So how do people typically do this? Well, as I said, you can actually build these on the same physical infrastructure, okay? But equally, you can also put separate networks in. So in this example, the cluster network itself, down in the green at the bottom, is effectively using 40 gigabit, and all of the communications from one cluster node to the other is actually taking place over that separate network. But the front-end network can actually scale out, and in this example we have 40 gigabits coming out of the Ceph cluster storage network and then separating out into 10 gigabit network in terms of the public connectivity, so that it actually scales dynamically. That's quite key. Actually having a nice non-blocking architecture for your client network gives you huge flexibility in terms of how you actually scale the Ceph storage cluster over time. And as you can see here, it's not necessarily a price point or a difficult price point question. You know, we were deploying, you know, the connectivity components at around $350 per terabyte. And actually, if you look at something equivalent to what you may historically do for block storage with fiber channel, that is significantly cheaper. So in this example, here's some of the headlines. So the cluster network was running at 40 gigabit. It offered really smooth, high availability across the network. There was no issues associated with the heartbeats, and it was offering very, very efficient data balancing. So if there was failures or any scenarios associated with the actual overall cluster, it actually rebalanced itself extremely quickly. Equally, the throughput at the clients guaranteed high line rate ingress and egress into the actual cluster itself, but ultimately that network then scaled out to individual clients at 10 gigabit. So we put the performance where it was needed at the storage tier, but ultimately we put a more cost-effective network in place at the client tier. And as you can see here, we did some various testing associated with this. And actually, when you look at 1 gigabit, 10 gigabit, and 40 gigabit as comparisons, obviously the actual performance of the overall cluster scaled very nicely. The bars themselves are associated with the bandwidth or the throughput, okay? And the actual lines, or the line, shows the IOPS per second. Now you'll notice here that there is actually quite a ratcheting off of the performance of the IOPS per second, okay? That is something that we've identified, and actually I'll show you what we're developing in terms of Ceph now to actually address that, okay? Hello.
Do you have any rough figures on the number of servers and ISPs to sort of that performance?
Yes, if you look here, there's a link to the PDF, okay, and actually that will give you all the details. I think it was about 500 clients in this particular example, so it was a pretty big storage cluster, okay. But if you put it, you know, to put it in comparison, if you deployed something on 1 gig and compared that with a 40 gigabit Ceph cluster network, as the headline says, we were talking about 20 times the throughput, 4 times the IOs, and actually it allowed a much better scalability over the actual life cycle of the cluster itself. So, what are we doing? Okay. Today, Ceph does all of its communications over the front end to the clients and also the back end to between its cluster nodes over TCP. Okay, well known, well trodden path. However, TCP invokes interrupts on the actual server nodes themselves, and it has to be packaged by the actual node itself. So the TCP packet has to be constructed and it ultimately has to be put onto the wire. Mellanox has a technology that's called RDMA. RDMA stands for Remote Direct Memory Access. So rather than using TCP, it's basically making a remote memory-to-memory communication. That could be memory to storage controller, or it could be storage controller to storage controller. This technology is actually an industry standard. It's been around for many, many years. Okay, but it's now coming into the mainstream enterprise marketplace. RDMA was originally developed for an InfiniBand network. Okay, however, it now can operate over a standard Ethernet network. That's called RoCE, RDMA over Converged Ethernet. And last month, Mellanox finalized with Microsoft and other parties the next generation of RoCE, which is RoCE, which is routable RoCE. So you can now send remote RDMA communications over extended networks. You can put it over WAN circuits. You can put it over layer 3 networks. So it's a lot more scalable in how you actually deploy this. Okay, so this is where we're going. So what does it do? As you can see in these diagrams, it makes a lot more, or it makes better efficiency of the actual user resources. There's less penalty paid in the actual processing of the data, or getting that data onto the wire. Pardon me. So specifically for Ceph, note the coming soon here, we're working on RDMA enabling Ceph clusters. Okay, we're using a free open source tool set that Mellanox has developed called Excelio. Okay, and this allows it to be extensible. So we can extend this over time, and if there's a new or other protocol that offer benefits or bigger benefits to customers, that can just be slotted in. But in reality, you can see here that the application tier, or the actual Ceph cluster software, ultimately won't change. It just allows you, it just sits on top of this tool set. Yes, we're using the RDMA transport today, but as you can see, TCP and other transports will follow. So it allows you to pick what you would like to do over time. So as you can see here, our first attempt was to look at the XIO messenger, or actually to looking at a replacement for the simple messenger with XIO. Okay, and you can see here that we managed to take the simple messenger, or compare that with the XIO messenger, I should say, or the replacement, significantly higher. So it shows that we can actually scale the bandwidth significantly through the utilization of RDMA in these techniques. Okay. However, not all was perfect. Okay. One of the things that we did find that, yes, just because we can solve the networking layer in this stack means that we actually move on to the next bottleneck. Okay, and actually, when we fixed XIO Messenger, that actually it's now opened up other challenges that needs to be addressed in the software stack, and that's being done. Okay, so we will, over time, you're going to see a lot of work that will improve these figures. But as you can see here, if you look at Ceph TCP compared with Ceph RDMA, yes, there's been an improvement, but in truth, it's not the same dramatic improvement as when we were looking at the messenger. This is where we've hit another challenge, and that's what we're addressing now. So expect these figures to improve, but this is a snapshot of time. So what I just wanted to reiterate is there is a very renewed focus on this, because we've now identified these other gates that we have to cross. There is this weekly community call that's very, very performance focused. So I would rapidly expect these performance challenges to be removed from the code and actually to allow the same kind of scalability that Excelio offers between the simple messenger and the XIO messenger. So watch this space is what I'm saying.
So when you say that, are you talking about the Mellanox driver code? Something like that?
No, obviously performance is relative. We can fix something in the Mellanox driver code, but it will move on to maybe some other challenge somewhere else in the stack. So actually, it's a community meeting, and we're addressing performance across every layer of the stack now. So that's why it's got to be we've got to take performance from a holistic point of view, because otherwise it doesn't make sense.
So it's driver, OS, and
it's driver, it's OS, it's Ceph, it's operating system, it's it's looking at it from top to bottom. Okay. So finally, Mellanox also does a lot of work in actually. Sorry, yes.
Just a quick question about Excelio. There's a precedent for this in the RDMA space, which was SDP, Sockets Direct Protocol, which Mellanox was also relatively heavily involved in the OFIF stack.
Yep.
An issue that SDP always had was that because the IP stack specifically in Linux is so well tested and has such a broad use case, and basically all the corner cases ironed out, SDP in TCP streaming applications was often actually slower or had equivalent performance than just using TCP over IP over InfiniBand.
Yep.
So how is Excelio different?
Okay, so we're now getting into some technicalities. So SDP is the Socket Direct Protocol, but essentially what it was a shim layer that captured the TCP call, and actually wrote that over an RDMA communication. That's essentially what it did. But the actual application itself still had to deal with TCP, still had to package the TCP, and then the call was made by the application that was captured by the shim layer. Okay, Excelio is different. Okay, Excelio is a programming API layer. Okay, so it's you have to code your application to take advantage of Excelio. You can't use something like an SDP shim layer or a TCP kernel bypass. Okay, it is a set of APIs. It's not complicated to use, but what I would advocate, if you're interested in this, Excelio is completely open source. If you go to excelio.org, there's a white paper on it, there's the programming schema, there's instructions on how to use it, but it's essentially you've got to code your application. Now this is what Ceph is doing. Ceph is going to be coded to use this API. Okay, so any application that sits on Ceph can obviously take advantage of this. Okay, so this is not something you've got to do as users, and actually is being taken care of by the community, but it's actually fundamentally different to how SDP worked. Does that answer your question? I know I haven't gone into details, but if you're really keen, have a look at the website. Okay. So finally, one of the other things that Mellanox does, and specifically my role in Mellanox, is actually trying to help organizations commercialize these kind of techniques and these products and these portfolios. So in here we've just got 4 examples that fit different verticals, and they're completely different from one another how they've actually architected it. But as you can see here, there's very, very scalable performance over the entire solution stacks, and they are very vertical tailored. So for example, Storage Foundry is very, very designed to capture video frames and video performance files at scale, at performance. So this is one way that you could easily consume Ceph today. You can actually go to these commercial propositions and take advantage of these tailored solutions that already have proven solutions in the marketplace. That's not to say that you can't roll your own, and we would actually advocate and we would actually willingly help you do that if you wanted to do that.
So these are all using Ceph under the hood?
These are all using Ceph under the hood. Okay, so in summary, the interconnect is actually quite important. It does drive scalability of your Ceph cluster. It can also obviously have a direct impact on the availability. Having a very fast back-end cluster network does give you that smooth HA, does give you that fast failover or that mitigation or the movement of those data assets. Yeah, Mellanox today obviously supports interconnects as low as 1 gigabit all the way up to 56 gigabit. Next month, or in fact in December, we're going to be able to do everything from 1 gigabit all the way up to 100 gigabit down a single cable. Yeah, so we are scaling our performance with the market need. So, you know, that drives a very, very cost-effective TCO case when you're building these clusters. And I'll happily have some conversations offline if people are interested. We are working with Red Hat, Inktank and others with the RDMA enablement we've got so far. It is already having benefits in the actual Ceph clusters, but obviously that's now identifying other things that we want to address, and ultimately you should see much more scalable performance of Ceph as a solution going forward. Okay, that's 25 minutes in. So, is there any questions?